Imagine, for a moment, sitting inside a spacecraft built for one purpose: to go faster than anything humanity has ever conceived, to challenge the ultimate boundary of the universe itself. You tighten the restraints, hear the systems hum, and you know exactly what the mission is. Push forward until you reach the speed of light. It's a simple goal in words, but in physics, it's the most extreme limit nature imposes on anything made of matter. This video isn't about superheroes blasting through galaxies or fictional ships snapping into hyperspace. We're going to take a grounded, scientific look at what the laws of physics say would actually happen to you and the universe around you as you approach the speed of light, and what those laws say about why you can never truly reach it. No drama, no exaggeration, just the strange, beautiful, deeply counterintuitive reality that emerges when you push Einstein's relativity to its edges. Before we dive into the heavy physics, let's frame the question clearly. When people ask, what would happen if I traveled at the speed of light, they're usually imagining a personal experience. What would I see? How would time feel? What would the universe look like rushing past me? Those are reasonable questions, but the truth is that the laws of physics make this scenario much stranger than it seems. As we'll see, the universe does not respond gently when you try to chase light. Light speed isn't just a very fast speed, it's a fundamental constant baked into the structure of reality. Photons, particles with no rest mass, glide along at this speed, and everything about how space and time behave depends on that number. 299,792,458 meters per second. It's not negotiable, not adjustable, not something you can bargain with. It simply is. And that's what makes this thought experiment so interesting. If the universe sets a limit this rigid and this absolute, what happens if you try to press up against it anyway? What happens as you move faster and faster and faster? What happens to the flow of time around you? What happens to the shape of space? What happens to the stars, the light, the radiation, and even the structure of causality, the chain of cause and effect that keeps reality ordered? Over the next hour, we're going to break this down step by step. We'll start with the rules, what physics allows and what it doesn't. Then we'll walk through what you'd feel on board your ship as your velocity climbs toward light speed, what the universe outside would look like, and why the experience becomes increasingly alien the faster you go. We'll explore the real, measurable consequences of relativity and the hypothetical scenarios people wonder about, from warp drives to FTL travel. But before any of that, we need to understand one thing clearly. The journey toward the speed of light is less about moving quickly and more about confronting the way the universe actually works. And the closer you get to the cosmic speed limit, the stranger that universe becomes. Before we begin, please consider leaving a like on this video and subscribing to the channel. Your support is greatly appreciated. With that out of the way, let us begin. Before we talk about what you would experience as your spacecraft accelerates toward the speed of light, we need to establish the framework that governs everything that follows. Relativity isn't something you can bend with clever engineering or brute force. It's built into the fabric of reality itself. And if we're going to explore what happens as you push toward light speed, we need to understand the rules the universe enforces, strictly, consistently, and without exceptions. Let's start with the most important fact of all. The speed of light in a vacuum is constant. It doesn't matter where you are, how fast you're moving, or what direction you're traveling. Every observer in the universe, no matter their motion, will always measure light moving at exactly the same speed, 299,792,458 458 meters per second. This isn't a measurement error or an approximation. It's one of the deepest truths physics has uncovered. This simple rule is the heart of Einstein's theory of special relativity. At first glance, it seems harmless, but once you accept it, everything else follows. Time dilation, length contraction, the energy blow-up as you approach light speed, and the absolute impossibility of any object with mass actually reaching it. These effects aren't quirks, they're the natural consequences of keeping the speed of light fixed for all observers. So let's break this down into the core principles we'll rely on. 1. The invariance of the speed of light. The first principle says, no matter who you are or how fast you're moving, you will always measure light speed as the same value. Imagine you're standing still and shining a flashlight. The beam leaves you at light speed. Now picture someone else zooming past you at half the speed of light. Intuitively, you might think that to them, your light beam would appear slower, like how someone running behind a thrown baseball sees it traveling at a reduced speed. But that intuition fails completely at high velocities. Instead, both of you measure the same number. Light doesn't slow down or speed up depending on the observer. This is the fundamental engine powering all relativistic effects. 2. The relativity of time. Once the universe commits to a constant light speed, time loses its role as a universal synchronized river. If two people move at different velocities, they experience time at different rates. This is not interpretation or theory, it's experimentally confirmed. Particle accelerators, GPS satellites, and high-precision clocks have all verified time dilation. The rule is simple. The faster you move relative to something else, the slower your time flows compared to theirs. This is why traveling near the speed of light effectively turns your ship into a time machine. You move forward in time more slowly than the rest of the universe. 3. The relativity of space. The universe doesn't stop at bending time. It bends space as well. As your speed increases, distances shrink in the direction you're moving. This is called length contraction. From your perspective inside the ship, the distance between stars literally gets shorter the faster you accelerate. This isn't an illusion. It's a direct physical consequence of preserving the constancy of light speed. Space and time must reshape themselves so that no matter how fast you're going, the speed of light never changes. 4. The energy curve. The next rule is unforgiving. As your velocity increases, the amount of energy required to continue accelerating rises dramatically. At normal human speeds, this effect is invisible, but as you approach a significant fraction of light speed, say 10%, 50%, 90%, the energy demand starts rising almost exponentially. By the time you reach 99.999% of light speed, the energy needed to push even slightly faster becomes enormous. At the limit, approaching the speed of light itself, the required energy shoots toward infinity. This is the universe's hard stop. It's not a technological barrier, it's a mathematical one. 5. The light cone structure. Finally, there's the structure of space-time itself. Relativity sorts events in the universe into 3 categories relative to you. Inside your light cone, reachable, causal. On your light cone, signals traveling at light speed. Outside your light cone, forever inaccessible without exceeding light speed. This structure determines what you can influence and what can influence you. As your speed increases, this cone tilts and distorts from your perspective, reshaping what counts as now elsewhere in the universe. The closer you get to light speed, the more warped this causal boundary becomes. Taken individually, these principles seem abstract. But once combined, they form a simple but powerful message. You're not just moving through space when you accelerate. You're reshaping your relationship with time, distance, energy, and causality itself. These are the rules of the game. Everything else, what you see, what you feel, what happens to the universe around you, flows directly from these principles. Now that we've set the foundation, we can finally step into the spacecraft and start accelerating. Now that we've established the rules the universe plays by, we can finally step into the spacecraft and begin the journey. We're not jumping straight to light speed, because physics simply won't let us. Instead, we're going to move steadily through the stages of acceleration, watching how the world around you changes as your velocity approaches the ultimate cosmic limit. This is where relativity stops being an abstract concept and becomes a direct, tangible experience. For clarity, imagine that your ship is capable of producing a constant, comfortable acceleration. Something like 1g, the same force you feel standing on Earth. If you kept that acceleration up, you would reach extremely high fractions of the speed of light in a matter of months. But the exact timeline isn't the point right now. What matters is the progression of phenomena that unfold as you move faster and faster. We'll break this down chronologically, following what you would experience inside the ship and what's happening in the universe outside. In the early stages of your journey, nothing feels unusual. You accelerate past the typical planetary and interplanetary velocities, tens of kilometers per second, and everything appears normal. Even as you reach 1% of the speed of light, roughly 3,000 kilometers per second, your senses and instruments don't register anything strange. Relativistic effects exist even here, but they're tiny. Time dilation might be a fraction of a percent. Length contraction is measurable only with highly precise equipment. To you, the cabin feels stable, calm, and ordinary. The stars outside look no different than before. The important point at this stage is that relativity is always in effect, but its consequences scale with velocity. At low fractions of light speed, the rules technically apply, but you're still far from the region where they dominate your experience. As you cross the 20% mark, things begin to shift. You won't feel these effects directly. Relativity doesn't work through physical sensations, but your instruments will. Clocks on Earth will begin to drift relative to your onboard time. Signals from home will look slightly slowed down. The delay isn't because of distance alone, it's because your time is starting to diverge from Earth's. From inside the ship, space still looks mostly familiar. You'd notice a subtle forward brightening of the star field. This is the beginning of relativistic aberration, where light from all directions starts to skew toward the direction of your travel. It's not dramatic yet, but you may notice that the stars in front of you seem more numerous or slightly shifted. Time dilation starts to become meaningful at this speed. At 40% of light speed, you age just a bit slower than the rest of the universe, maybe seconds or minutes over the course of days. Still subtle, but growing. When you pass the halfway mark toward light speed, relativity stops being subtle. This is the region where the universe begins to look unmistakably different. At 50% of light speed, time dilation is measurable on the scale of minutes and hours. For every hour you experience, someone stationary relative to your starting point might experience perhaps an hour and 10 minutes. As you push beyond 70% or 80%, the difference grows quickly. You feel nothing unusual internally. Your heartbeat and breathing remain steady, but your ship's clocks drift further out of sync with external time. A video message sent to you from Earth would arrive appearing slightly slowed down because your relative time has changed. Length contraction becomes important now. This effect doesn't mean that you feel crushed or squeezed. It means the universe along your direction of motion compresses from your perspective. A star system 10 light-years away might now appear only 9, 8, or fewer light-years distant depending on your speed. This shortening of space is what makes near-light travel so tempting in science fiction. As you move faster, distant destinations genuinely become closer. For you, the star field outside begins to shift dramatically. Stars that were originally off to your sides gradually slide forward. By the time you reach 80% of light speed, the majority of visible stars seem to cluster toward a cone in front of the ship. This isn't an illusion or tunnel vision. It's caused by the way light's direction transforms between reference frames. As your speed increases, photons arriving from sideways or even backward directions get re-angled into the front. The universe begins to visually narrow. This is the range where things become extremely strange and extremely beautiful in a quiet, unnerving way. Relativity's effects here dominate your entire experience. At 90% of light speed, time moves about twice as slowly for you compared to someone who remains stationary. At 99% of light speed, your time runs at roughly 1/7 the rate of an outside observer. Push to 99.9%, and 1 hour for you might be dozens of hours for everyone else. At 99.999% of light speed, 1 day for you could correspond to years passing outside. Your personal time inside the ship remains smooth and normal, but the universe is rapidly moving ahead without you. A star 100 light-years away might now appear only a few light-years distant from your perspective. In principle, you could cross what would normally be centuries of travel in a matter of years or even months of your own time, depending on your speed. This is one way relativity allows interstellar travel without violating the light speed limit. You're not going faster than light, the distance is shrinking in your frame. As your speed climbs, the light ahead of you becomes blue shifted. At moderate speeds, this simply makes stars appear brighter or slightly more energetic. But at very high speeds, the blue shift becomes extreme. Visible light shifts into ultraviolet, then X-rays, then gamma rays. Even the cosmic microwave background, normally harmless, faint and cold, becomes dangerously energetic when blue shifted this severely. Your ship now needs extraordinary shielding to protect you from the radiation blasting in from the direction of travel. At 99% and above, nearly all visible light from the universe collapses into a bright, narrow forward cone. Behind you, everything dims and redshifts into invisibility. You are no longer surrounded by stars. You are staring into a brilliant, compressed, high-energy point of distorted starlight ahead of you. As you reach 99.9999% of light speed, the curve becomes brutal. Every incremental increase in speed demands exponentially more energy. Distances contract further. Time dilation spikes. The universe around you becomes almost unrecognizable. Most importantly, you can approach the speed of light arbitrarily closely, but never reach it. Your energy requirement approaches infinity. The laws of physics remain firm, but by this point, the effects you're experiencing are already far beyond anything in everyday life. You've stepped into the domain where space and time bend around your motion, where distances warp, where time slips out of sync with the rest of the cosmos, and where even the stars themselves appear to gather into a single shimmering point directly ahead. This is the threshold between ordinary motion and the fundamental edge of physical law. Next, we'll explore what the universe looks like from inside the ship as you cruise at these extreme velocities, not just what changes physically, but what changes visually. The view becomes one of the strangest sights imaginable. As your spacecraft settles into a high relativistic velocity, something beyond 90%, 95%, or even 99% of the speed of light, the physics we've discussed stops being theoretical and becomes a direct sensory experience. This is the point where the universe no longer resembles the quiet, familiar star field you've known your entire life. The rules of relativity don't just alter measurements and equations, they rewrite the visual texture of reality itself. To understand what you would actually see, we need to look at three major effects working together: relativistic aberration, Doppler shifting of light, and the transformation of the cosmic background radiation. These aren't optional phenomena, they're unavoidable consequences of your motion, and together they give the universe a strange, almost otherworldly appearance. Let's start with the most immediate and striking shift: relativistic aberration. Under normal circumstances, light reaches your eyes from every direction, forming a roughly spherical pattern of illumination. The stars appear scattered across the sky in every direction. But as your speed increases, the apparent direction of incoming light begins to change. When you're moving at 90% of the speed of light, starlight that originally came from your left, right, or even slightly behind you gets bent forward into the direction of your motion. The higher the speed, the more extreme this effect becomes. By the time you're at 99% or above, almost all visible light collapses into a single forward-facing cone. The universe looks as if it's being pulled ahead of you, squeezed into a bright, compact patch of sky. Behind you, the star field fades, stretches, and eventually disappears entirely from the visible spectrum. You're no longer surrounded by stars. You're following a narrow, bright corridor through space-time. This isn't a matter of perspective or illusion. It happens because the direction of incoming photons transforms between reference frames. In your ship's frame, photons that originally had sideways or backward trajectories now arrive with forward-leaning angles. Space is still out there, but almost all of its visible light has been funneled into the direction you're traveling. The next effect is equally dramatic: Doppler shifting. This determines not only the colors you see, but also the amount of radiation striking your ship. As you move toward incoming light, its wavelength becomes compressed, the same principle that changes a siren's pitch when an ambulance races toward you, applied to light instead of sound. At high relativistic speeds, red light shifts into yellow, green, and blue. Blue light shifts into ultraviolet. Ultraviolet shifts into X-rays. X-rays shift into gamma rays. So the cone of starlight ahead of you isn't just visually concentrated, it's rapidly becoming more energetic. If you accelerate far enough, the visible universe ahead of you can transform into a blinding, high-energy haze. This is one of the biggest physical hazards of relativistic travel. Even ordinary starlight becomes dangerous, and the faster you go, the more extreme the energy becomes. Behind you, the opposite happens. Light is stretched into longer wavelengths. Visible stars dim into infrared points, then microwaves, and eventually radio waves. The rear view becomes dark and cold, not because the stars cease to exist, but because their photons no longer fall into any visible or near-visible band. The universe behind you essentially evaporates into darkness. Under normal circumstances, the cosmic microwave background, the leftover radiation from the early universe, is a faint glow at about 2.7 Kelvin. Its wavelengths are long and harmless, completely invisible to the naked eye. But at 99.9% of the speed of light and beyond, the CMB becomes blue-shifted into higher energy bands. At extremely high speeds, anything approaching the speed of light to several decimal places, the CMB becomes intense. From your perspective, what was once microwave radiation becomes infrared. A bit faster, it becomes visible light. Faster still, it becomes ultraviolet. Eventually, it becomes X-ray radiation, and at extreme speeds, it becomes gamma rays. This isn't subtle. If your ship lacked advanced shielding, the blue-shifted CMB alone could deliver lethal radiation doses long before stray starlight did. This is one of the most overlooked realities of relativistic travel. At these speeds, the universe becomes physically hostile. The fabric of space-time itself becomes a constant stream of high-energy particles and photons slamming into your ship. When you combine aberration, blue shift, and red shift, the view from your window becomes a coherent but alien panorama. Ahead of you, a bright, compressed, blue-shifted tunnel of high-energy radiation and distorted starlight. To the sides, faint stretched stars being drawn forward like streaks of pale light. Behind you, near total darkness, with everything red-shifted out of visibility. It's not a tunnel in the science fiction sense. It's simply what happens when space-time itself transforms how light reaches you. The experience is strangely peaceful, but deeply unearthly. You're still moving smoothly, without turbulence or vibration, because space is nearly empty. But visually, you're watching the cosmos distort and reshape itself in response to your motion. The universe is no longer a stable dome of stars. It's a dynamic, shifting pattern governed by relativity. Despite the intensity of all this, your personal experience remains calm. Inside the ship, nothing feels strained. Your heartbeat remains normal. Your sense of time remains steady. The distortion of the universe is entirely external, a transformation of how space-time delivers light to your eyes. This contrast is one of the most fascinating parts of relativistic travel. You feel nothing, but everything you see tells you the universe is behaving differently. The visual distortions are not hallucinations or artifacts. They are the exact way reality must appear when you move through it at such extreme velocities. From here, the next step is to shift inward, to examine what you experience personally as your own passage through time diverges from the rest of the universe. That's where relativity becomes intimate. After observing the strange and distorted universe outside your ship, it's natural to wonder, what about you? What does it feel like to travel at relativistic speeds? Surprisingly, the answer is subtle, even gentle. Unlike the extreme visual and physical transformations occurring outside, your own experience remains remarkably ordinary, at least inside the ship. Relativity reshapes the universe around you without directly altering your internal sense of time or motion. Inside the spacecraft, your clock ticks as usual. You eat, breathe, and move with the same rhythms you always have. From your perspective, an hour aboard the ship is just an hour. Your heartbeat doesn't race, your metabolism doesn't slow, and your perception of the passage of time remains entirely normal. The universe outside, however, is on a different schedule. Due to time dilation, observers at rest, relative to your starting point, experience time faster than you do. A trip that feels like days or weeks to you could correspond to years, decades, or even centuries outside, depending on how close you approach light speed. In essence, your personal frame of reference stretches time for the rest of the cosmos. This creates a profound, almost poetic consequence. You become a time traveler, not because you move faster than light, but because the flow of time differs between your frame and that of everyone else. Despite the extreme speeds and warped universe outside, the interior of the ship remains calm and familiar. There's no vibration, no shaking, no sense of rushing through space. The effects of acceleration that could harm you are kept constant and safe. You can walk through the cabin, manipulate controls, or observe instruments without any sudden jolts. Relativity does not act on you in a direct, tangible way. You do not feel compressed by length contraction, nor do you perceive the forward blue shift as heat or force. The laws of physics affect how external light and energy reach you, but your own body and environment exist in your local frame, which remains stable. Your journey emphasizes the contrast between subjective and universal experiences. To you, the stars ahead may still appear a bit brighter, and distances may seem slightly shorter, but the effects are subtle unless you are extremely close to light speed. However, when you glance at distant destinations, you realize that, in the rest of the universe, time has continued far more rapidly. Entire civilizations could rise and fall while only a few days pass for you on board. This creates a remarkable paradox. You are moving quickly through space relative to the universe, yet moving more slowly through time relative to everyone else. The personal experience is smooth, calm, and ordinary, while the universe itself stretches and ages beyond your perception. What makes this stage of travel so compelling is how it illustrates a profound truth about relativity. Extreme effects are often invisible from the inside. You live normally, yet you exist in a context where every second of your life corresponds to far more time outside. You are intimately connected to the universe, but your personal frame isolates you from its ordinary flow. In this sense, relativistic travel is both peaceful and alien. It allows you to move across vast cosmic distances in a time frame that feels manageable, while the universe outside accelerates at an unimaginable pace. Your senses remain calm, your thoughts clear, and yet you are witnessing a quiet reshaping of reality around you, a universe subtly bending to the demands of light-speed motion. Next, we will examine the ultimate hard limit: why, no matter what, you can never actually reach or exceed the speed of light, and what that tells us about the deep structure of space-time itself. As we've seen, accelerating toward the speed of light transforms the universe around you in remarkable ways. Space compresses, time slows relative to the outside, and radiation from the cosmos becomes increasingly energetic. But now we reach a crucial question. Why can you never actually reach the speed of light? This isn't a technological limitation. It's a fundamental boundary written into the laws of the universe. Understanding this limit requires examining energy, mass, and the structure of space-time itself. The first and most straightforward barrier is the exponential growth of energy required to accelerate an object as it approaches light speed. According to special relativity, the kinetic energy of a moving object isn't simply proportional to its velocity in the familiar Newtonian sense. Instead, it follows a more complex relationship that rises steeply as velocity approaches c, the speed of light. At low velocities, energy requirements grow predictably. Double your speed, and you double your energy, roughly speaking. But once you approach significant fractions of c, this linear relationship breaks down. The closer you get, the more rapidly the required energy escalates. By the time you reach 99.9% of the speed of light, you need many times more energy than exists in an entire planet or even a star to push just slightly faster. As you speed up, the energy needed to keep accelerating grows rapidly. There's a simple way to describe it mathematically. Your energy equals your mass times the speed of light squared, divided by the square root of 1 minus your speed squared over the speed of light squared. Now, that might look complicated, but the idea is straightforward. As your velocity gets closer and closer to the speed of light, the bottom part of that fraction gets smaller and smaller. And when that happens, your energy skyrockets. It shoots toward infinity. In other words, the faster you go, the more energy you need. And trying to reach the speed of light would require an impossible, endless supply of energy. No matter how advanced your ship or engines are, you just can't get there. It's not a matter of technology, it's a fundamental law of the universe. A related concept is the idea of relativistic mass, which reflects how an object's effective resistance to acceleration grows with speed. In your frame, your rest mass stays constant. But from an external observer's perspective, your momentum increases dramatically as your speed rises. The faster you go, the more massive you appear in terms of how much energy is needed to accelerate further. At 50% of light speed, your relativistic mass is modestly higher. At 90%, it's already more than double. At 99.9%, it becomes enormous, effectively making further acceleration impossible with finite energy. This reinforces the same conclusion. Light speed is unreachable because your momentum would have to be infinite. It's important to emphasize that this doesn't mean your body feels heavier inside the ship. You would not sense this mass increase directly. But physically, every attempt to push past the speed limit encounters a boundary that cannot be crossed. Energy and mass aside, light speed represents an absolute boundary built into space-time itself. The speed of light is woven into the geometry of the universe. Photons, particles without rest mass, travel at exactly this speed, and all massive objects exist in a separate category. Their world lines in space-time cannot reach the light-like boundary. This has profound consequences. Causality is preserved. If massive objects could exceed light speed, they could travel backward in time relative to some observers, creating paradoxes. For instance, an effect could precede its cause, violating the fundamental order of events. Relativity remains consistent. Allowing faster-than-light travel would break the mathematical structure of Einstein's equations. Length contraction, time dilation, and the invariance of light speed would all fail catastrophically. In short, space-time itself forbids exceeding light speed. It is not a guideline, it is a geometric law. Photons illustrate the boundary clearly. They have no rest mass, which allows them to travel at light speed without requiring infinite energy. Their motion is natural for massless particles. You, by contrast, have rest mass. Any attempt to push you to light speed encounters the infinite energy barrier described earlier. This distinction explains why light can propagate through the vacuum, while you, as a material object, cannot. The laws of physics treat massless and massive entities differently, and this difference is absolute. Physicists have speculated about particles called tachyons, which would move faster than light. But tachyons remain hypothetical for good reason. They violate causality. Their energy equations produce imaginary numbers, reflecting the breakdown of conventional physics. No experimental evidence has ever suggested their existence. If tachyons existed, they would belong to a separate class of entities that cannot slow down to sublight speeds. You, with mass, remain strictly confined to sublight velocities. These limits have practical implications. Interstellar travel remains long-term. Even if we can accelerate close to light speed, reaching other star systems still requires careful planning. Distances contract in your frame, but from an external perspective, centuries could pass. Energy demands dominate. Any propulsion system capable of approaching C must supply energies far beyond current technology. Concepts like nuclear or antimatter drives are speculative and would still face these exponential requirements. Radiation hazards intensify. As you approach light speed, the universe itself becomes energetic and hostile. Cosmic microwave background radiation blue shifts into dangerous X-rays and gamma rays. Shielding becomes essential even before you consider reaching the absolute limit. The impossibility of reaching light speed isn't a limitation. It's a profound statement about the structure of reality. By enforcing a strict speed limit, the order of cause and effect is preserved. Energy, momentum, and mass retain consistent relationships. Space and time remain intertwined in a mathematically consistent framework. In short, light speed defines the boundary between what matter can do and the ultimate propagation of information in the universe. It is a cosmic guardrail, keeping physics consistent and predictable. To summarize, accelerating toward light speed requires more energy than can ever exist. Relativistic mass grows without bound, preventing further acceleration. Space-time geometry enforces an absolute speed limit. Only massless particles, like photons, can move at light speed. Hypothetical faster-than-light motion would violate causality and the structure of relativity. No matter how fast you accelerate, light speed is the asymptotic horizon, an unreachable edge. You can get arbitrarily close, experience the strange distortions of space and time, and witness the universe warped around you. But the laws of physics draw a firm line, ensuring that the cosmic speed limit remains unbroken. This limit is not a failure of technology or imagination. It is the universe's elegant, absolute law. Understanding it deepens our appreciation of relativity, energy, and the intertwined nature of space and time. Next, we will explore the thought experiments and hypothetical scenarios that arise when we push physics to its extreme. Imagining what could happen if we cheated the rules or used theoretical concepts like warp drives and wormholes. Now that we've seen why reaching the speed of light is physically impossible for objects with mass, it's natural to wonder, what if we could cheat the rules? What if we could bypass the energy barrier or manipulate space-time itself? These scenarios are purely hypothetical, yet they reveal fascinating insights into the structure of the universe and the extreme consequences of relativity. We'll explore them step by step, from near-light speed travel to speculative faster-than-light concepts. Even though we cannot reach light speed, physics does allow objects to approach it arbitrarily closely. A spacecraft traveling at 0.9 c or 0.99 c would still be subject to all relativistic effects, but the experience is manageable with enough energy and shielding. As discussed previously, near-light speed travel compresses distances in the direction of motion. For example, a star system 100 light-years away in the rest frame of Earth may appear only 10 or 5 light-years distant from the perspective of a ship moving at 0.99 c. This is the practical effect of length contraction, which allows for interstellar travel in human-scale timeframes, at least from the traveler's perspective. Meanwhile, time dilation slows your passage of time relative to the universe. A trip that feels like a few years for you could correspond to centuries for observers on Earth. The faster you go, the more extreme the discrepancy. Near light speed travel doesn't break the rules. It works within them, exploiting the geometry of space-time itself. The main obstacles are energetic and environmental. The ship requires enormous propulsion energy to maintain extreme velocities. Radiation hazards from blue-shifted cosmic light and interstellar particles increase dramatically. Structural integrity of the craft must withstand potential collisions at relativistic speeds. Even so, near-light-speed travel is theoretically possible within Einstein's framework, offering a glimpse of what future interstellar exploration might achieve. Moving beyond conventional travel, scientists have speculated about manipulating space-time itself through concepts like the Alcubierre warp drive. In this model, a spacecraft doesn't move faster than light relative to its local space-time. Instead, space-time in front of the ship contracts, while space-time behind expands, effectively transporting the ship across vast distances without locally exceeding the speed of light. Imagine a bubble of space containing your ship. Within the bubble, your velocity remains sublight, but the bubble itself moves faster than light relative to the rest of the universe. In principle, you could traverse hundreds of light years in a matter of months from your perspective. The warp drive requires negative energy densities, which may not exist in usable quantities. The energy demand is staggering. Estimates suggest the mass-energy equivalent of entire planets or stars. The front of the bubble accumulates radiation during travel, creating a lethal environment when the ship exits. Warp drives remain a theoretical construct, illustrating that even if physics allows clever manipulation of space-time, the practical challenges are astronomical. Another hypothetical approach is a wormhole, a tunnel connecting two distant points in space-time. A traveler could theoretically move instantaneously between locations without moving locally faster than light. Wormholes require exotic matter to remain open. Without it, they collapse or pinch off, making passage impossible. Even if we could stabilize one, navigating a wormhole safely presents extreme hazards from tidal forces and gravitational distortions. Wormholes could, in theory, connect different times as well as places. This introduces causality paradoxes, which are why wormholes remain speculative and constrained by the same principles that prevent faster-than-light travel for massive objects. The concept of tachyons, particles that move faster than light, illustrates why even hypothetical, faster-than-light motion is fraught with challenges. Tachyons violate causality, meaning effects could precede causes in some frames. Their energy equations are imaginary, reflecting an internal inconsistency in physics. There is no experimental evidence for tachyons. For these reasons, faster-than-light travel for objects with mass remains firmly in the realm of thought experiments rather than engineering. Even in hypothetical cheating situations, certain truths remain consistent. Relativity cannot be broken. Any mechanism must operate within or alongside the constraints of space-time. Energy demands are extreme. Whether accelerating near light speed or manipulating space-time, the universe imposes a heavy energetic toll. Causality matters. Faster-than-light travel or time manipulation threatens the order of events, creating paradoxes that challenge the consistency of physics. These scenarios show the elegance of the universe's limits. While imagination allows us to explore exotic ideas like warp drives, wormholes, or tachyons, they illuminate why the speed of light remains the ultimate boundary. For a traveler, near-light speed experiences would feel smooth and ordinary. Yet the universe itself would behave in ways completely alien. Hypothetical constructs like warp drives or wormholes highlight how our intuitions about motion, distance, and causality break down when we leave familiar scales. They remind us that even with clever thinking or futuristic technology, the fundamental rules of physics govern every step of our cosmic journey. To summarize the "what if we cheated" scenarios, near-light-speed ships work within relativity, allowing interstellar travel with time dilation and distance contraction. Warp drives theoretically manipulate space-time to exceed apparent light-speed motion without violating local physics, but demand unimaginable energy and negative matter. Wormholes could connect distant points in space-time instantaneously, but face extreme stability and causality challenges. Tachyons and FTL particles remain speculative and inconsistent with established physics. All of these thought experiments deepen our understanding of relativity and space-time, illustrating both the incredible possibilities and the strict limits the universe imposes. They allow us to explore extremes without breaking the fundamental rules that make the cosmos coherent and predictable. Even though physics tells us that an object with mass can never reach the speed of light, it is still instructive to imagine what would happen if you could. This is a purely theoretical exercise, a way to explore the ultimate limits of relativity and the strange behavior of space, time, and light at the edge of what's physically possible. At light speed, time behaves in an extraordinary way. According to special relativity, as your velocity approaches c, time dilation grows without bound. If you could somehow reach c, your personal clock would stop entirely. From your perspective, no time would pass. You would exist in a state where all events in your frame are frozen, a cosmic pause. For an outside observer, however, you would appear to continue moving at light speed, traveling across space while time ticks normally for them. This creates a profound asymmetry. You experience neither past nor future, while the universe continues inexorably around you. Length contraction is another extreme effect that would reach its limit at light speed. In your frame, the distance between any 2 points in the direction of motion would collapse to zero. The stars, galaxies, and interstellar voids ahead of you would be compressed into a single infinitesimal point. From a practical standpoint, this means that, in theory, you could traverse the universe instantaneously, at least in your own frame of reference. But this is a thought experiment, not a feasible journey. Reality enforces the limit. Distances can shrink, but reaching c would require infinite energy. The visual experience at light speed would also be unimaginable. Aberration would focus all incoming light into a single, forward-pointing point. The universe behind you would vanish entirely. At such speeds, blue shift effects would turn visible light into gamma radiation, while cosmic background radiation would also become extreme. You would be engulfed in high-energy photons coming from every direction ahead. In practical terms, exposure to this radiation would be lethal. But as a thought experiment, it illustrates how the universe fundamentally transforms at the speed of light. Reaching light speed also touches the limits of causality. For massive objects, approaching CE rearranges the order of events relative to outside observers. At sea, the concept of a cause and effect sequence in your own frame becomes meaningless. Another reason why physics forbids massive objects from attaining light speed. The universe enforces a boundary to prevent paradoxes and maintain logical consistency. Even though it is impossible, imagining light-speed travel deepens our understanding of space-time. It highlights the absolute nature of the cosmic speed limit, the extreme consequences of time dilation and length contraction, the intimate link between energy, mass, and motion, how the universe enforces causality and the structure of reality. By stretching the laws of physics to their ultimate limits, we gain insight into why the universe behaves the way it does. Even impossibilities illuminate the fundamental beauty and consistency of relativity. Having explored the limits imposed by the speed of light and imagined the impossible case of reaching it, we can now return to a more practical, though still extreme scenario: traveling close to light speed. This is where the effects of relativity become meaningful, but still allow for a human-scale experience. Understanding these consequences is essential for considering the potential of interstellar travel and what it would mean to experience the universe at its ultimate speed limit. As we've discussed, near-light speed travel dramatically slows the passage of time relative to stationary observers. This means that, from the traveler's perspective, journeys across the galaxy could take years or decades rather than millennia. For example, imagine a spacecraft accelerating to 0.99 c toward the nearest star system beyond our solar system, Proxima Centauri, located 4.2 light-years away. From Earth, it would still take just over 4 years for light to travel that distance. But due to length contraction, the distance in the traveler's frame shrinks. Instead of perceiving 4.2 light-years, the ship might measure only 0.6 light-years. From the traveler's perspective, the trip could take less than a year, depending on acceleration and deceleration. This difference is one of relativity's most striking consequences. The universe feels smaller, and distant destinations become accessible within a human lifespan, even if the external universe experiences far more time passing. The traveler's subjective experience of space remains surprisingly calm. The ship moves smoothly, and there is no direct sensation of rushing through the void. However, the visual universe becomes extraordinarily distorted. Stars in front of the ship appear compressed into a bright, narrow cone. Colors shift due to Doppler effects, with forward light moving into ultraviolet or X-ray frequencies at extreme speeds. The cosmic microwave background radiation blue shifts, bathing the ship in high-energy photons. Outside this cone, the universe seems to vanish. The rearward star field redshifts and dims, effectively disappearing from visible perception. While internally everything feels normal, externally, reality behaves in a way that is fundamentally alien. Traveling at near light speeds introduces unique challenges. Even tiny particles of dust or hydrogen atoms become significant hazards as they collide with the ship at relativistic energies. Shielding must account for high-energy cosmic rays and blue-shifted starlight, interstellar medium impacts, which could erode or penetrate conventional materials, radiation from the cosmic background, which grows increasingly dangerous with velocity. Navigation is also complicated by relativistic aberration. Light from stars and celestial objects no longer arrives from predictable directions. Traditional star maps become distorted, and onboard instruments must account for these relativistic transformations. At near-light speeds, communication with home becomes increasingly difficult. Time dilation means that signals you send are received out of sync with your own perception. A message sent to Earth might arrive decades later in your frame, while Earth observers would receive it in a much shorter interval relative to their own clocks. This has practical implications for interstellar exploration. Real-time communication across stellar distances becomes impossible. Mission planning must consider asynchronous timing. The traveler becomes increasingly isolated from Earth's frame of reference. In essence, near-light speed travel disconnects you from the normal cadence of the universe. even as you move through it safely. The profound temporal asymmetry between traveler and external universe raises deeper questions. You could witness centuries passing outside while experiencing only a few years. Entire civilizations could rise and fall while your subjective timeline remains brief. The universe becomes simultaneously accessible and unreachable. Distances shrink, yet time outside continues relentlessly. This duality makes relativistic travel not just a physical challenge, but a philosophical one. It forces us to reconsider our understanding of time, aging, and the human experience in a universe governed by relativistic laws. Even with the possibility of approaching light speed, the constraints remain severe. Energy demand: the closer you get to C, the more energy is required. Achieving 99.999% of light speed would demand far more energy than exists on any planet or star. Radiation hazards: the universe itself becomes an energetic threat, requiring extraordinary shielding and engineering. Causality and isolation: time dilation and communication delays mean travelers exist in a nearly self-contained frame, fundamentally separate from the universe they left. These challenges ensure that, while near-light-speed travel is theoretically fascinating, it remains a monumental engineering and practical problem. Traveling close to light speed transforms both space and time in dramatic ways. Distances shrink, making faraway stars feel within reach. Time slows relative to the rest of the universe, creating an asymmetrical temporal experience. Visual perception of the cosmos becomes intensely distorted, with extreme blue shifts and aberrations. Radiation and particle impacts impose serious physical hazards. Communication with the outside universe becomes asynchronous, emphasizing isolation. In essence, approaching the speed of light allows humans to bridge vast cosmic distances in a subjective time frame, but at the cost of extreme energetic, observational, and psychological challenges. Relativity ensures that no matter how advanced technology becomes, the universe preserves its structure, its causal order, and its ultimate speed limit. As we conclude our journey through the possibilities and limits of light-speed travel, it is worth stepping back and reflecting on what these thought experiments reveal, not just about physics, but about our place in the universe. Relativity transforms the familiar notions of space and time. As velocity increases toward light speed, distances shrink and time slows relative to the universe. Stars and galaxies, once distant and immutable, appear closer and more malleable from the traveler's frame. Yet the universe itself continues relentlessly, emphasizing that motion is relative and that our perception of reality depends on our frame of reference. The impossibility of reaching light speed highlights the elegance of nature's laws. Energy requirements grow without bound, relativistic mass increases, and space-time itself enforces an absolute limit. Even when we imagine bending the rules with warp drives, wormholes, or tachyons, we confront fundamental constraints: causality, energy, and the geometry of the cosmos. These boundaries are not limitations of imagination. They are the consistent, predictable rules that make the universe intelligible. At the human scale, near light-speed travel offers fascinating possibilities. Distances become manageable, and journeys across the galaxy can occur within a traveler's lifetime. Yet the experience remains profoundly isolating. Time outside the ship accelerates, the universe visually distorts, and communication with home becomes asynchronous. Relativity transforms not just space, but our relationship to time, civilization, and the cosmos itself. Ultimately, exploring what would happen if you traveled at light speed is more than a scientific exercise. It is a meditation on the structure of reality, the constraints of nature, and the delicate interplay between human perception and the universe. It reminds us that even the impossible, reaching the ultimate speed limit, can illuminate the beauty, consistency, and wonder of the cosmos. Thank you for joining us on this journey into what it would be like to travel at the speed of light. The universe is vast, full of wonder, and always moving in ways we are only beginning to understand. We'd love to hear your thoughts. Leave a comment with questions, ideas for future videos, or what fascinates you most about space. Take care and never stop exploring.